In a previous video, you might remember that anytime you have a charged particle entering a magnetic field, it experiences a force which changes its direction. Related to this phenomenon is the idea that anytime you have a force, so to speak, a voltage, oomph, pushing a charge through a wire, you can create a magnetic field. And that magnetic field will surround the wire. If you were to put a very small compass as close as you could next to a wire carrying direct current, you would see a deflection of the needle. If you tried to do this with a compass next to a wire that's plugged into an outlet, because the electricity in the outlet is alternating, that is to say, oscillating back and forth 60 times per second, you would not record any magnetic field because it's expanding and collapsing too fast for the compass to register. Look at the picture on the left. The beige or khaki colored area is a circle, but you're looking at it from the side, so it appears to be an oval. Running through the center of that circle is wire number 2. And that circle represents a slice of space in which you have a magnetic field at that particular point in the wire. That magnetic field is represented by the green circle. If you were to use your right hand and point your thumb from left to right, you can see on the back side of the wire, your fingers are curling up and point towards you at position B, representing the green arrow B2. In other words, they would be going, the magnetic field would be going counterclockwise if you were looking at that from the right side of the page. Now, the magnetic field established around wire 2, because there's current going in it, will affect the wire number 1 that is above it at a distance d above wire 2. We know that the strength of a magnetic field, B2, is proportional to the amount of current, I2, in wire number 2, and it's inversely proportional to the distance that you are from the center of the wire, D. That's this equation right here, which we looked at in a previous section of the chapter. Now, coming down to the bottom equation, we are going to take the equation that says that the force acting on a wire in a magnetic field, F equals BIL, we're going to substitute for that magnetic field B2. When we do that, we get the equation at the very right that says the force that wire number 1 is going to experience equals mu sub aught, that's the permeativity in free space. That's the ability of that space to hold a magnetic field, times current number 1 in wire number 1, current number 2 in wire number 2, times the length that those two wires are parallel to each other, divided by 2 pi times the distance between them. If we divide both sides by that length, that the two wires are parallel, we get equation 19.14. The direction of the force that F1 is going to exert is downward, using your right-hand rule, meaning if you put your thumb in the direction of the current in wire number 1, your fingers, either above the page, or below the page, or inside the page, will be represented by your curled fingers surrounding the wire. As a result, parallel conductors that carry currents in the same direction will attract each other, because in the space between the two wires, if you use your right-handed rule, you get magnetic fields that are opposing each other, and opposites attract. And conductors carrying currents in opposite directions would repel each other, because those magnetic fields would not be opposite each other. We can use this equation actually to define what an amp is. We can also use it to define what a coulomb of charge is. Example 19.18 is an interesting problem in that, let's say we want to levitate one wire above another. So we have two wires. They each have a weight per unit length of about a 10,000th of a Newton per meter. The wires are 1/10 of a meter apart. And if you look at the solution, we want the sum of these forces to equal 0, the gravitational force acting down, the attractive force acting up. They're in opposite directions. We want them to equal each other so that we get the levitation effect. Because they're in opposite directions, we'll choose the weight, the gravitational force, to be negative, and the other force, the levitating force due to the current in the wire and its resulting magnetic field, to be positive. We set those equal to each other, and we solve for I squared. When we plug our information in, remembering that 4 pi times 10 to the minus 7th Tesla times meter, which is in the denominator, is our, if you come back a little bit, is our mu, permeativity in free space right there. That would be given to you. That's a constant. We see that the current in each wire needs to be 7 amps about in order for one wire to be able to offset gravity in the other wire. And you would get levitation. And 7 amps is about half the amount of current that a typical wire in a wall outlet would be allowed to have, because they are on 15 amp fuses or circuit breakers. Now you can imagine that if you have a single wire going in a loop, you're going to have a very small magnetic field. The direction of that magnetic field would depend upon the direction of the current in the loop. If you look in the upper left-hand picture, and you have your curled fingers following the red arrow of the current, you'll notice that your thumb of your right hand will be pointing directly upward, meaning that your magnetic field would be going from north at the bottom of the loop to south above the loop. We could make that effect greater and greater by having a second loop and a third loop and a fourth loop and so forth. We call these multiple loops a solenoid. And you can have solenoids of literally thousands of loops of wire, concentrating the magnetic field and creating a very, very strong electromagnet. An electromagnet is simply a coil of many wires, a solenoid, in other words, with direct current going through it. If you look at the green lines representing this magnetic field in the second picture, figure 19.30, you can see that your magnetic field lines about a solenoid, picture A, mimics or mirrors or looks very similar to the magnetic field lines about a permanent magnet. So you can have a permanent magnet based upon the properties of the material that makes up the magnet, usually some amount of iron. And you can have an electromagnet that is created by electricity going through a wire in a solenoid. The electromagnet, of course, you can turn off by turning off the current. A permanent magnet, you would not be able to turn it off. We can calculate the strength of this magnetic field B because it would be dependent upon the number of turns of wire. If you were to double capital N, the number of turns of wire, all things being equal, you would get a doubling of B, the magnetic field of the electromagnet. It also depends upon the current I. If you were to double the current, all things being equal, you would double the strength of B, the electromagnetic field. It's inversely proportional to R, the distance of the wires from the center of the solenoid. That's why we like to use very, very thin wires so we can pack them really close together. Thick wires, especially because they have to be coated in insulation, pushes the wires farther away from each other, and it begins to weaken the overall effect of your electromagnet. But of course, if you have thin wires with very thin insulation and you try to have lots of current going through it, you end up heating up those wires substantially. And you might even get some of that current to penetrate the very thin insulation. My first experience with electromagnets was way back in grade school when I built that robot for my 6th grade science fair project, and the right hand of the robot actually was an electromagnet that I could raise and lower to pick metal things up off the floor. And it was just a nail with a bunch of wire wrapped around it, and the wire was connected to a battery. Again, this coil of wire with multiple loops is called a solenoid or an electromagnet. If you change the direction of the current in the wire, you change the magnetic field. If the North Pole was at the top, now the North Pole is at the bottom. And again, if you look at a picture of a solenoid with the green field lines representing the magnetic field created by the electricity going through the wire, and you look at the pieces of iron, the very, very fine iron filings suspended perhaps in oil, on top of a solid permanent North Pole, South Pole bar magnet, you get a very similar looking kind of picture. The strength of this magnetic field then again is dependent upon the current. It is also dependent upon the number of turns of wire. But here we're using the lowercase n, where the lowercase n represents the number of turns of wire per length. We could kind of define this, if you will, as the density of the coil in terms of number of turns of wire per length. These electromagnets used to be used in the old-fashioned television sets, where a beam of electrons was fired from a source towards the screen of the television set, and in order to tune or direct that beam of charged particles, of electrons, you would control it by having electromagnets along the x-axis and along the y-axis. So you could strike the surface of your television screen covered in phosphors that would glow any place you want. We also can use this to direct an electron beam in an electron microscope at a target. Particle accelerators can also cause an electron beam to accelerate. Mass spectrometers do the same thing. And of course, everybody loves a good mass spectrometer. Back in Idaho. Looking at example 19.9, part A says, find the magnitude of the magnetic field. Well, in order to use the equation that says B equals the permittivity of free space times lowercase n times I, you have to find the value of n. And incidentally, this is a common mistake students make on a test, is forgetting that lowercase n is the number of turns of wire, capital N, divided by L, the length of the wire. Notice that your answer is in Tesla, which is the one way to measure the strength of a magnetic field. Part B says find the momentum of a proton. In order to do this, we take F equals ma, Newton's second law, and set it equal to F equals qvb from earlier in the chapter. When we substitute out A by substituting in centripetal acceleration, v squared divided by r, because remember, the charged particle is going to be traveling in a circular path, and so it's going to experience centripetal acceleration, we get this equation that mv squared over r from centripetal force equals qvb. Solving this equation for mv, we get momentum, because mass times velocity is momentum, if you remember that from second quarter. Finally, how much wire? Well, simply, if you have the length of your wire, it's going to be the number of turns of wire going in a circle, 2 pi r, and you're going to need over 30 meters of wire to make this solenoid. Now, just like you can have a magnetic field above and below the solenoid, a North Pole and a South Pole, you can also talk about a magnetic field inside the solenoid. And indeed, there is a lab, which we may or may not be able to do, either virtually or in the laboratory, where you investigate the magnetic field inside and outside of a solenoid. And in this lab, the solenoid is actually a slinky. If you don't know what a slinky is, you'll have to Google it. In this picture, imagine that we have a solenoid. Look at the picture on the right, which looks kind of weird, but you're going to have to think about this. Along the left side of the picture, you have all of these gray circles with orange dots. Each one is a cross-section of a wire that is carrying current coming out of the page in your face, so to speak, outward. It curls around, which of course you can't show in a flat surface, and enters on the other side of this picture, going down into the page, and there you see the tail end in an orange X representing the current going down into the page. And so every dot coming out and X going down represents one loop of your solenoid. And you have about a dozen X's and dots here representing about a dozen loops. And you're looking at a cross section of that, a slice of the solenoid. And the magnetic field will be going from the north at the bottom of the picture to the south at the top. By convention, magnetic fields go from north to south, hence the direction of the green arrows. You can use your right-hand rule, and if you point your thumb in the direction of B, the natural curvature of your fingers in the right hand go down into the page on the right side of the green arrows and come out of the page up into your face on the left side of the picture. The last part of this chapter talks about the theory behind what is a magnetic field. What creates it? What is it about the structure of an atom that makes a magnetic field possible? And some of this is kind of theoretical. I actually talked about this a couple of weeks ago when I showed the iron atom with its 26 electrons, and I did the 1s2, 2s2, 2p6, so forth. And we looked at the fact that in the d orbital, you have d subshell, you have 5 orbitals. And you put 1 electron in each orbital before you put the second electron in each orbital. And it's based upon the idea that you learned in chemistry that an orbital can only hold 2 electrons as long as one of the electrons has a spin that is opposite of the other electron. Since the 2 electrons would naturally repel each other because they have the same charge, if they have opposite spins, they would have opposite magnetic fields, and therefore they would be able to attract each other, opposing or canceling out the effect of the electrostatic repulsion. Now, the spin of an electron is a convenient description that we sometimes use in quantum mechanics. It's the 4th quantum number for those of you that took AP chemistry. So you can get a magnetic field created by a moving electron translationally or in a curved path, but also a magnetic field about the electron if it's spinning. 2 kinds of motion: the physical movement of the electron from point A to point B, and the spinning of the electron on its axis. And again, spin is an idea that is only understood in the context of quantum mechanics. It also reminds us that you can only put 2 electrons in an orbital. And the idea here is if you have several orbitals that only have 1 electron in them, and all of those electrons are spinning in the same direction, the magnetic field of each orbital is augmented by the magnetic field of the other orbitals because they're all spinning in the same direction. And you get the sum of those magnetic fields. Instead of all the magnetic fields canceling each other out because you have random spins in different directions, you can get an accumulative magnetic field. Such a material would be said to be ferromagnetic. And of course, iron is very, very common in this phenomenon. Hence, we have the prefix ferro, which is the Latin word for iron. When you get huge regions all spinning in the same direction, all coupling together their magnetic fields, we call this region a domain. And if you can get all of the domains to align evenly, then you create a permanent magnet. This is the domain theory behind magnetism. And as you can get more and more of those arrows for more and more of those domains pointing in the same direction, you begin to increase the overall magnetic effect of the material. So the strength of an electromagnet would be increased dramatically if you take your solenoid, your device that is creating the magnetic field, and you put an iron core through the center of your solenoid. This concentrates the magnetic field, so to speak, and your electromagnet becomes much, much stronger. Remember, I said that back in 6th grade, my first experience with electromagnets was a coil of wire that I had a nail going through it. Actually, I did it the opposite. I took the nail and then wrapped the coil around it as tightly as I could, creating my magnetic field, my electromagnet. So again, a ferromagnetic material can be a permanent magnet where it would retain its magnetic properties over time. Some materials, if you bang them on concrete or something, you can actually unalign the domains and it will lose its magnetic properties. Paramagnetic materials are very weakly magnetic. Recognize that word para. For example, a paralegal would be a person who isn't exactly a lawyer, but assists the lawyer. They're like a weak lawyer, though they're very, very important in the law field. A paramagnetic material would be very weak. Such paramagnetic materials would be like aluminum and calcium and platinum. Now, paramagnetic materials you might use to study because if you heat them up, and this would be true for any ferromagnetic material, at some temperature you get hot enough and you unalign all of the domains and you lose your magnetic properties. That temperature is called the Curie point or the Curie temperature. There are also some materials, interestingly enough, that actually appear to be diamagnetic. They are very, very weakly opposed to a magnetic field, repel a magnetic field. And you can see in the picture 19.40, figure 19.40, levitating a frog in a super, super strong magnetic field. Remember, the Earth's magnetic field is about a 10,000th of a Tesla. Here you have 16 Tesla. And of course, this is a very, very technologically and biologically important phenomenon to be able to levitate frogs. The world needs levitating frogs. Sarcasm. You can conclude your study of this chapter by going over these essential ideas as summarized in this page.